Swayam Prabha. Digital India. Educated India.
Welcome back. In the previous session, we saw that we started talking about L type, and also we have seen that certain things are not allowed, certain things are blocked by L type. We have also seen that an adverb, like if you have something like S goes to S and ADV, and then S goes to N and VI, and this is, say for example, this is John smokes, and then here you have restlessly. We have seen that this is not a, we have already talked about this. This is not a good structure. Why isn't it a good structure? Syntactically, it seems that it is fine. But so if this is the structure, then we can see that the type would be T to T, because this is T and this is also T. So it would be T to T. But what makes us say that T to T is not the type for this adverb, or any adverb for that case? It is basically an argument we already mentioned in one of the previous sessions. That is, the adverb cannot take 1 or 2 as a truth value. What it does is it can take it should take a 1 plus predicate, and then once again. So as I said, it should be this type, E to T to E to T. So it should take 1 plus predicate like smokes, and after that, that will once again take another function, like for example, suppose John smokes and John smokes restlessly, but at the same time Tom smokes, but he doesn't smoke restlessly. So it will map Tom to 0 and John to 1. So first it will take the normal predicate, that is sleeps, and then it will take this one, and once again it will finally take an argument like John. If John smokes restlessly, it will yield 1. Now this is an old argument, but we need to talk about it because it is now connected with its type. So we are trying to establish the point that these adverbs cannot be T to T, but they are this thing. So yeah, then we refer back to that argument, the one we did in a previous session. So but now also we can, before we start looking at this abstract language called L type, we can also determine a few other types, and then we can get back to it. For example, we can have something like somebody from somewhere. We are not interested in the structure of from, but we are interested in the structure of not in the structure, but the type of from. So for example, suppose there is a sentence, the student from Kanpur is good. So it will be something like this, S, then you have this whatever, the student from Kanpur, and then you have good, which is VI. So N will be student from Kanpur. So what is the internal structure of this? It will be another N, which goes to the student and here you have, which is another entity, and you have here kind of a PP prepositional phrase, which will be the P, which is from, and another N, which is Kanpur. Now, what is the type of from? We can just see that. So, the calculation is pretty straightforward and simple. Definitely, this is T. We know the type of this. It has to be an E, and this has to be an E to T. All 1 plus predicates, that is VI's, are E to T, and so this is E, and once again Kanpur would be E, and the student, it's an entity, it will also be E. But then what will happen finally? What will be the type of from? So because this is E and this is E and this is E, this PP has to be E to E, otherwise, so it has to take an E and yield an E. But then what will be the structure for from? It takes an E and then it gives back an E to this one. So this will be the structure of things like in, from, where two entities are connected to make another N. So this will be the type for from. So this is one, and a few others. This we're just computing the type of a lexical category helps actually determine its structure, its features, like other features of the category. That's why we first compute the type. We need to do that because now on the type would be the most important identity of any linguistic element. So we have seen that this is something like this, and then we can also see a little more. For example, you have something like malfunctions, for example. So you can say that the machine malfunctions, right? We are interested in the structure, in the type rather, of mal, not anything else. So S, and then you have something, the machine or whatever, doesn't matter what. And here you have the VI, which is malfunctions, which once again goes to VI, and another modifier which is actually mal. So what will be the type for this? Once again, it's very easy. We know that this is T and this is E. Therefore, VI as usual has to be V to T, and VI is once again, so functions is also V to T. So then what will be mal? It will be this type, E to T to E to T. This will be the type for mal. So this is how we compute now. We can compute the types of a lexical item. So then we now we can enter the abstract field of L type, and we can see the structure of our language. So we know the basic operations, which are these. So as usual, DE is A, and DT, yesterday also we talked about it. For any syntactic categories A and B, DAB is this, that is a function from DA to DB, and this is, now we start. So we may remember that in the previous session we talked about a specific language, L1. We in fact we rewrote it from the type theoretic perspective. Now we are actually doing the language L type. Now in this we are not assigning types to any specific lexical item. We are just coming up with general rules. As I said, this would be proper higher order predicate semantics. We cannot just talk about one predicate. we now need to talk about all predicates possible and all entities possible, ideally infinite predicates of infinite types. For example, predicates, predicates of predicates, predicates of predicates of predicates, and everything. So we now should be able to talk about predicates, not just about entities. Now, definition: E is a type, T is a type. If A and B are any types, then AB is a type. Nothing else is a type. This is like the old system. So once again, just it's kind of a recap. Yeah, so the first thing we can have is E to E, because E is a type. So E to E will be a type following 3, or T to T, or E to T, or T to E. We have also seen that T to E is normally not seen anywhere, and T to T is very common. E to T, of course, is very common, and because E is a type and E to T is a type, we can always have E to T. So now we can see that we have a full-fledged recursive system. We can make any type out of this, but then the rules will block certain things. Basic expressions. Now, as I already said, we are not talking anymore about M and B one-place predicates and two-place predicates like K or L. We are talking about all one-place predicates and like all two-place predicates, and also we are talking about their predicates. So basic expressions: for each type A, the set of non-logical constants of type A denoted con A. Con means constant, contains constants C n A for each natural number n. So A is the type and n is the number. So for example, following this, C 0 E is a constant. It is the 0th constant, if you put it that way, of type E, and then same type, but you change the constant. So you have C1 E and so on. So C n E. So you go to the next type, you can have C0 E to T. So this is a constant of say of one. This is a one-place predicate. So it could be M, and then suppose C1 E to T. Suppose it is B. I'm not saying that these are M and B, but just I'm trying to give a picture, a specific picture, so that we get the abstract picture well. And what will be the time for K and L, which are two-place predicates? They would be, for example, they could be 0 E to T. Suppose this is L, and then C1 E to T. Suppose this is L and this is K. So these are constants. We are not dealing with variables right now. For each type A, we are talking about rule 2. For each type A, the set of variables of type A denoted var A contains variables v n A, similar for each natural number n. So these are constants, and correspondingly we could have v 0 E and stuff, also v 0 E to T. So this is a variable for any one-place predicate, and v 0 E to T. This is a variable for any two-place predicate. So it can go on. It can be of any type. That's why this is abstract. Now, as I said, this is higher order predicate calculus. It is because we can now construct things like these and things like these. We are not confined anymore to just these three types, and we had just one type previously, this variable. We didn't have anything like this or this. Now a variable of this type will range over all one-place predicates, and like this one will range over all two-place predicates. So So these are about constants, non-logical constants and variables. Then syntactic rules. ME stands for meaningful expression. For each type A, every variable and every non-logical constants of type A is a member of MEA. So, for a type, all its members belong to that very type. For example, let us talk about 1 plus predicates e to t. So, all variables, so all constants, for example, take let us assume that this means m, and we know that now m will belong to me e to t, and also all variables of the same type would be members of this, that this also will belong to me e to t. Okay, so we go to the next rule 2. For any types A and B, if alpha belongs to MEAB and beta to MEA, then alpha beta will belong to B. Now, this is the blocker. This is a very, very important rule. This allows only things like, so a type E to T can take only an E, nothing else. And a type E to T can take only E and nothing else. So, this is a rule about the argument types. So, if a function has a certain type, this rule will determine the arguments of that function. For example, now something belonging to type E, for example, C0E, this will not be used as a function anywhere, because there is nothing that comes out. Now, this, as I said, this is a blocker, and we needed this blocking. So, now what is now possible? You can have something like, yes, if there is an ME to T, it can take an E as an argument. If it is T to T, then it can take only a T as an argument and nothing else. So, we have already set up a rule which works as a blocker. So, then the next rules in fact 3 to 7, if phi and xi are in MT, that is, if they are sent their formulas, then so are each of the following: nec phi, phi and xi. So, all logical operators will come here, all of them would. So, if phi belongs to phi and xi belong to MET, then all of these will belong to MET. And if alpha belongs to MEAB, now this is a general rule, and u is a variable, then all u phi also belongs to MET. And I think here I think we should have alpha instead of phi. I think we should have alpha here. So, as we said that we need a variable to work now. So, what is the lowest? It has to be A to B structure. That is, it can either be E to T or it can be E to E to T, but it doesn't work for a standalone type. For example, for T it doesn't work, for E it doesn't work. So, the point is, if alpha belongs to A to B and u is a variable, then all u alpha belongs to MET. For example, let's take an alpha m. So, if m is if this is a structure, then this will be by this will be a sentence. it's perfectly all right. So we don't have to change this. So phi and both the phi's here are actually t-type things, and this phi contains an alpha. So for example, look at this structure, all u, all x, mx, because in this case, or for us the variables now are v1 and stuff like that. So yeah, I correct myself. So yeah, this is perfectly all right. The typing, I all the time get scared thinking that I typed something wrongly. Okay, so the point is this phi should contain this alpha. So for example, take m, which belongs to me e to t, right, because it's a 1 plus predicate, and in that case phi would be, say, m v0 e, has to be, because this is an entity like x. So v0 e stands for an entity, and if this is the case, then as we have seen, u is a variable. So here our u is this. In that case, for all v0 e, m v0 e would be also a formula, and the same applies to sum. Okay, and then we go to the semantic rules. So if alpha is a non-logical constant like any other language like L1, if it is a non-logical constant, then f will assign it a value, and if alpha is a variable, then g is going to assign its value. We know this, and then this corresponds to the main rule, that is, if alpha belongs to MEAB and beta belongs to MEA, then alpha beta, the value of alpha beta will be alpha that takes beta as an argument, practically the value of alpha that takes the value of beta as an argument. And this is like L1, we don't have to do this again. And now this is very important. If alpha belongs to MEAB and u is a variable, then all u phi with respect to mg is 1 if and only if for all e in dA, it has to be dA, the first one. You remember that the u must belong to A, and alpha must belong to AB. We know that. So if in this structure, or in the new version, our structure would be, so if this belongs to E, this has to belong to E to T. We know that from the rule, from the construction rule, that is rule 2, the syntactic rule 2. And if for example L belongs to ME E to E to T, right? So I may sometimes omit the comma. So L belongs to this. So in that case, our variable has to be once again E. It cannot take anything else. So this is something which is very important. We need to consider this. So in this case, so for example, I give an example of this. Say B V0 E. Now we know that B belongs to E to T, and V0 E definitely belongs to E. It is explicitly belongs to E. This is a good construction, but we cannot have, for example, B that is banned because both belong to E to T. So this is not a good construction. Or definitely we couldn't have BX because this is T and this is E to T. Remember, it has to take only E. So by our rules, these constructions are prohibited. So and then finally, if alpha belongs to MEAB and u is a variable, then it is about sum. We know this stuff. I'm not reading this again. So denotation relative to model M, we have seen that in every language that there is a final thing where we just get rid of the G in our formula, and it is nothing. Just by computing g, we can do this. So yeah, I don't want to repeat this. So now we need to see how does this help us. As I said, I talked about blocking. Now this, a construction like this is banned. What is the implication of this? Now the implication is actually very great. For example, I now cannot say that it is false that L, and then for example my statement, if you like, my statement. You cannot construct something like this. This is like all my statements, all my sentences, all my prepositions are false. So if you like, you can also make it F. Now this construction is impossible, because suppose it has this form. Now, and we give this a type. Let us call this type, I don't know, just some random thing. Let us call this type A. Now if this is the case, then if the whole thing belongs to type, so this thing, if this whole thing f(x) belongs to type A, then it cannot take f(x) itself as an argument. That is banned, because they belong to the same type. So so for example, as I said, that all my prepositions are false. So now there is a typical mismatch. Some predicate cannot take its own type as an argument. So same. So if f belongs to A, then it cannot take f(x). It cannot take f(x) as an argument anymore. So it cannot take itself. A predicate cannot take itself as an argument anymore. So this is banned. That's why you could never have a structure like this. So and without having a structure like this, you could so for example, it is false. So false is all my old prepositions are false, whatever. So so I could not now do this. So because if false has a certain type, whatever type it may be, then it cannot take itself as a predicate at all. So this construction, both false, is impossible. That is the reason this construction is blocked, and that is the reason liar's paradox is blocked in this system. So we go to the next slide. Some applications of our type theoretic language. We start with say, for example, non. What is non? Non as in non-violent, non-vegetarian, and all that stuff. Now non is defined here in a certain way. We first read the definition, and we then try to understand. In the beginning, the definition may look very complex and all that stuff, but if we read it once, all the complications will go. So non with respect to mg is that function h from d e to t into d e to t. That means it would be something like d e to t d e to t. So the function space is this, e to t to e to t, such that for any k in d e to t and any individual e in a, hk that takes e is 1 if and only if ka is 0, and hk as a function together takes e and yields 0 if and only if ke is 1. We will try to understand this definition by considering this case. So although this case is a specific case, the definition is general, and we will try to understand the general definition. So consider Mohan is non-violent. we are, remember, we are trying to determine the type of it, and we are actually defining non. So, two things we are doing at a time. We are determining its type and we are defining it. So, assume that Mohan is non-violent is 1. I am not here concerned very much with this MG. It is assumed that it will be like this, but I did not write. Now, what is the type for violent? Violent would belong to meaningful expression MEE to T. It is a 1 plus predicate, because if I said that Ramu was violent, then I would use this structure, right. So, it would be Ramu would be E and violent would be E to T. So, Ramu is violent would then be T. So, the same goes for non-violent. So, when I say Mohan or Ramu is non-violent, I am also doing the same thing. So, both violent and non-violent do belong to the type E to T. So, and then violent and Mohan is 0. So, Mohan is non-violent if and only if Mohan is not violent. That is, Mohan's being non-violent depends on his non-being violent. That is violent, Mohan this thing, that is violent is the function, Mohan the argument, this should give 0. So, let us compare this to K. So, if and only if K E, let us say that E is Mohan. So, then we consider this function. What kind of a function is this? It is H, and remember that H is now representing non. So, non-violent. So, non will first take violent and then that will take Mohan or anything. So, what is the structure of it? Our sentence is Mohan is non-violent. So, it goes to N and Vi, N goes to Mohan and non-violent goes to non-violent. Remember, we are not determining, we are not calculating the type of non-violent. We know that is Vi and that will be E to T. We are actually calculating or computing the type of non, and so this is non and violent. Now, violent is E to T. So, non is this function H which takes this function violent. So, what would be the type of non? It would be E to T to E to T. As I said, sometimes I am going to omit the commas. So, it is practically E to T comma E comma T comma E comma T. This is the structure. This takes violent and gives another function. So, what is this? This HK function is actually non-violent. How is non-violent cooked up? Non takes violent. So, one E to T function, that is H, takes another function K and yields another E to T function which is our HK. It is a combined function. Then that takes E, say for example Mohan, and then finally that yields T. So, that is how S belongs to T. So, just by comparing this, by comparing this example, this is non and violent. So, this is the combination of non and violent. This is a function, this is this function where this E to T to E to T takes an E to T, and that, so this finally yields this E to T function which is non-violent, that takes Mohan and finally yields 1, because Mohan is practically non-violent. So, compare this structure to this HK E, and also remember it is not HKE. We are not going to confuse these two structures. This is different. This is HK, that is one combined function, and that function takes E like this. It is not that non takes, it is not that violent first takes Mohan and then that is taken by non. That is impossible. Now, what is the mistake in understanding this as as the following. I will just see that. Suppose it is not this h k e, it is rather h then k, and that takes e. What is wrong with such constructions? So, is it okay? This is absolutely wrong, because we know that k is e to t. So, compare k to violent, and this is e. Now, e to t and e already gives t, and h then cannot belong. So, h need to belong to t, because this is t. So, what will be the function? And we know that the whole thing, that is Mohan is non-violent, has to be t. So, so this will be t. So, what will be the type for h? T to t, but that is not the case, right? That is not the case. Mohan is non is actually e to t, to e to t, which takes an e to t, thus it makes. So, this is e to t, to e to t, which takes an e to t and yields e to t, and that once again takes an e and finally gives a t. This is the working of the function, and this is how the definition goes here. So, this is about one definition. We will see a few type theoretic definitions. For example, this is about sometimes we use transitive verbs as intransitive ones. For example, you ask me, does Mohan eat rice? I just answer, he does. Now, imagine there is a machine that is dealing with all these sentences, but for that machine, eats is an e to t function. That is, this is the category assigned to eats, because eats needs two elements, the eater, this is the eater, and the object eaten. So, the machine knows that. Remember that we are not just writing a grammar for humans, also we are writing ideally a grammar for non-humans, intelligent machines. So, so the machines also should understand what is going on when somebody is talking. So, for example, you ask me, does Mohan eat rice? I answer, he does, which means, so the machine understands that does is a dummy verb which has to take the previous verb. So, in that case, it is actually Mohan eats. Now the machine will be confused. Why? Because for it, eats must take an object, but in Mohan eats there is no object. Mohan eats is just e to t. So, when we speak sometimes this way, the machine would be completely completely confused. It will have no understanding of these structures. So, then that is the reason we need to talk about this conversion, that is e to t to e to t. Sometimes we do convert. Now, that conversion itself, remember, we are not talking about eat or eat, both are. So, if this is eat 1, which is the transitive eat, this is the intransitive eat and eat 2. We are not talking about eat, we are talking about the transformation, the function that converts eat 1 to eat 2. We are talking about that function, and we name that function R0. Why R0? It is because we are here deleting the object of a transitive verb, and we are converting it to a. So, we are basically converting a VT to a VI. So, this conversion is R0. So, this is a function, and once again this function is h from the e to t, that is, compare this to eat 1, which is a regular transitive verb, into d e to t, which is eat 2, which is this sometimes irregular, occasional intransitive verb. When we say, for example, Mohan eats, we use this, such that for all functions k, now we are defining h, we need k for that. For all functions k in d, e to e to t, and all individuals e in a, h k e is 1. If there is some individual e prime in a such that k e prime e is 1. Once again, it looks complicated, but any abstract language, any abstract definition looks complicated. We need to decipher it through a specific case again. Let us assume Mohan eats, that is, Mohan eats is true. What does it mean? The construction of Mohan eats would be like this. Mohan eats is true if and only if Mohan eats something. Let us assume that he eats rice. So, what is the construction of Mohan eats rice? It is something like this. So, it is actually S goes to N and VI, VI goes to VT and N, N goes to Mohan and VT goes to eats. This is, remember, this is the regular eats, and N goes to. Now, what is the construction once again? So, this is the construction. I have written this in a linear form, but this is practically what I have written here. Now, K is eats. So, you see, this is the thing we are talking about. This is the regular eats, and this belongs to e to t like this. So, this is e. So, it has to be e to e to t, and this is once again e to t. This is e. So, finally, they yield t, like they yield e to t similarly. So, this is the construction. H converts eats 1, which is an e to t, into eats 2, which is just e to t. So, we are not talking about the conversion function. Remember, we are not talking about just eats, because eats, this eats has to be e to t. That is not our problem. We are talking about this function which we called R0. Thus, hk is eats, right, because h is the function which has converted eats 1 into eats 2. So, this is h and this is k. We compare these things. So, then what is h? So, this is what basically this is saying. Now, this is the function, now this is the type part. Then comes the definition part. So, h k e is 1. So, we just read it out so that we understand, such that for all functions k in the e to t and all individuals e in a, that is, we are talking about all 2 place predicates. So, we can say Mohan loves when Mohan loves somebody. We are going to say Mohan eats when Mohan eats something. In all these cases, then what will happen is there would exist a function h that will take any k, that is any 2 place predicate, and that will take an entity, Mohan or Ram, whatever, and it will yield 1 if and only if there is some individual e prime in a such that k e prime e is 1. Remember, this k prime, this k is actually the normal eats, which is eats 1, which is a 2 place predicate. And also remember that a function 2 place predicate first takes the object, then the subject. If we remember the previous sessions, we remember this: first object, then subject. So, so then this will be true, that is, the function will do a correct thing, that is, h takes k and e and yields 1, which precisely says that here this R0 function takes its normal and Mohan and yields 1. That is, we are now trying to say that Mohan that is this, we are talking about this conversion function. This function does a right job, even it is applicable if and only if there is some individual e prime in A, that is it's an individual such that k e prime e, this e, let this be Mohan and let this be Rice. So that this is the case. That means so the function that converts each to ETH will take these two things as arguments and yield 1 if and only if Mohan eats, this is eats 1 something. So, we just compare, thus h k is eats 2 and eats 2 takes Mohan and yields 1. Already this eats is an e to t function, if and only if if and only if there is some e prime Mohan eats, that is something he eats. There exists, that is there exists some e prime such that eats e prime Mohan is 1. That is now you see this is the 2 plus predicate. So, it is e to t and it first takes this e prime which is an e. So, it first takes Rice, then it takes Mohan, then it yields 1. If this structure is good, then this function R 0 is working correctly. It is applicable to eats, which is the regular eats 1. So, this is what the definition says. We go to the next definition. Once again we get back to the old example of machines. There is an artificially intelligent machine, and it for the first time hears that somebody says, it hears somebody say that Mira is liked. Now, you see like is used as a one plus predicate, although like is a 2 plus predicate. In a passive voice sentence, like is normally used as a 1 plus predicate. Now, there must be a function that converts the like 1, which is the regular 2 plus predicate, into like 2, which is a 1 plus predicate. Now, this is a subject deletion function, that is why it is called R s. Why is it so? For example, when it is true that Mohan likes Mira, you can say Mira is liked. The subject Mohan is deleted. So, these two steps just state that. Here R s m g is that function h from d e to t into d e to t, the same thing. So, the function space is pretty much the same. It takes an e to t, that is a 2 plus predicate, and converts that into a 1 plus predicate. But the conversion style, the conversion mode is now different, such that for all functions k and d e to t and all individuals e in A, h k e is 1 if and only if, that is the conversion function is applicable to k, in this case it is like, if and only if there is some individual e prime in A such that k e prime is 1. Once again it is this is the object and this is the subject is 1. We compare this to the structure to the structure of this abstract definition. We once again discuss a specific case to understand this abstract definition. Suppose Mohan likes Mira. It is true that Mohan likes Mira. Therefore, it is true that Mira is liked by some individual. We do not have to say all the time. It is enough that we say Mira is liked, like we say Mira is killed or John is killed. H converts likes, that is the normal likes 1, into the passive voice like to, like is killed, is liked, which belongs to MEE2T. Let K be likes, the normal like. So, Meera is liked is 1 if and only if there exists some individual E prime. So, we are just rereading this. There is some individual E prime such that E prime likes Meera. That is, there is some E prime such that likes Meera E prime. So, the object comes first, as usual, is 1. Otherwise, it is 0. So, this, remember that we are not talking about the function the vi like 2. We are talking about the conversion once again, the function that takes like 1 and converts that into like 2, as in is liked, as in is liked, from Mohan likes whatever, Meera, or any such structure. We are talking about that function and we are defining that function. So, we are just saying that that function h is applicable if and only if there is some individual E prime in A such that E prime holds that relationship, whatever K is, to the individual that is liked the object. So, precisely in our case it is so E prime is Mohan and E is Meera. So, this is how we talk about types, and now we want to read a few sentences to understand. Let us see how many are there. So, yeah, we cannot cover all this in this session. So, it will be slightly. So, in the next session we have to talk about it. So, we may consider one case and then see what happens. So, let us now try to understand this statement. What does it say? Now, remember that we promised that we would be able to construct higher order predicates, and here we do that. What is it? Now, first let us read the statement. It says that for all 1 plus predicates, you see, for all 1 plus predicates, is it talking about a specific 1 plus predicate like M or B? No, it is talking about any 1 plus predicate. I said that we shall be able to talk about predicates in general. We are doing that for all 1 plus predicates. If it applies to J, that is, if it is attributed or if it is predicated of J, then it is predicated of D. Now, in order to understand this, so if it is true of J, it is true of D. We need to understand, we need to consult the model to understand this. And in the model, so there are two things, J and D. So, J and D. So, J is the name for the individual A and D is the name for the individual B. Now, there are just two 1 plus predicates. What are those? M and B. So, precisely this is saying that if any predicate is true of A, it is true of B. So, because the denotation of J is A and the denotation of D is B. So, let us check whether that is true. Let us first consider, we have to just consider two cases. Let us first consider this. So, it applies, so it is from the direction is from J to D, that is from A to B, So, if M is, we shall check whether it is the case that if M is true of A, then M is true of B, definitely. M is true of A and M is true of B. It is not the case that M is true of A and not true of B. And let us now check. So, the second one does not apply to A at all, it applies to B. So, what is, so we just write that B Bj, what is the truth value of Bj implies Bd? There are two cases, right? One is because there are two things, two 1 plus predicates, we just need to consider two cases. First, Mj to first Mj to Bd, and then this one. Now, this we can see that yes, M applies to A and it applies. So, this is 1, this is 1. So, this will be 1. What is the matrix for if it is, for example, if alpha implies beta, we just remember the matrix 1 1 1 1 0 0 0 1 0, sorry 1 and 0 0 1. Now, we need to perhaps we need to also see the logic for this matrix. It is precisely because when I say that if A then B or if alpha then beta, I just make one promise. It is not the case that alpha is true, but beta is not true. Nothing else do I promise. For example, alpha is happening and beta is happening. Yes, the case is confirmed. The case of alpha implies beta. Suppose there is no alpha, still there is beta, which is perfectly all right. For example, when we say that if it rains, the soil gets wet, and we can see that even if it does not rain, the soil may get wet due to many other reasons. So, this is okay, and the fourth case is it is there is no rain and also the soil is not wet. So, this is also 1. Only one thing goes against this, if it rains then the soil gets wet, only one thing falsifies it. What is it? That is, it is raining, but the soil is not wet, everything else gives 1. That is the reason only this line gives 0, every other thing is 1. Now, this is the case of vacuous quantification. Why vacuous? Because we cannot the truth value of this part is 0, therefore, it will be 1. We do not even look at the truth value of beta, just because alpha is 0, the whole thing will be 0. So, Bj is actually 0 because j is A and B does not apply. So, B is not true of j. So, this will be 0. We do not have to look at this at all. Yes, we know the value of it, it is 1, but irrespective of the value it will be 1. So, we can see that there are two cases and in each case the truth value is 1. Therefore, this sentence is true for all 1 plus predicates. It must be the case that if it applies to j, it will apply to d. I think we need to do one last thing. The book has given a few problems we have not solved, and also it talks about the typical matching of things in lambda calculus. We need to cover just that part, and then we are done with most of it. So, we start with the type. We will see whether the types here match or not. So, how to check? You see, the tree construction can be sometimes very complicated. This tree will be somehow complex. It is not a very easy tree, but we can give types to the basic things. For example, we know that is this is e to t, we know this is e to t. Now, we remember that this is actually from the construction, this is the definition of all, and it was not that it was derived from, but we started this with this thing, all students walk. So, w x, and then we took out the predicates, the predicate constants, and we put two predicate variables q and p here. So, that is what we are doing. So, this is basically a lambda definition of all, and s and w added to that. So, with all these things, it is a sentence, right, because we have just split a sentence, a full statement to see how it works, and then p will be once again e to t, which is a variable, and q another variable, predicate variable. x is e, and this will be t to t to t. I'm omitting commas because commas are there anyway. So we know that all binary operators, binary logical operators, do belong to t to t type. So and then we don't know the types of these things. We can compute, but we don't need. The tree construction is actually very simple and also very complex. Sometimes we start computing here. So t and t give us t, t and t give us t. This is perfectly intuitive because this is like a sentence, like basically like a formula, and then this and this, that is, this is t to t to t, which takes a t and gives a t to t, and this t to t takes this t and gives another t. This is once again intuitively perfect because this is a sentence. This whole thing is a sentence and it should give a sentence. Now we can also see that this thing, whatever it is, whatever it may be, it takes a t and gives a t. So practically the type of this should be t to t. Now this helps us compute also types of things we don't know about, and then we go ahead. So we are now here, and now other constructions. For example, we start little above and then we see what happens. We go at this level, for example, the top level. So the whole thing we know must be a t because the entire thing is a sentence, right? So this whole thing, whatever it might be, takes an e to t and yields a t. So it must be an e to t type. There is no doubt about it. It takes an e to t and gives a t, and this once again is computed. This has taken actually this has taken another thing. This has taken another e to t and given this. So what is the type of it? It will be e to t to this thing. E to t will check whether this is correct or not intuitively, which is the most important thing here in this section. To t, yes, bracket closed. So now this will be just another type where it goes up to here, and then one thing is left out, that is this one. So till here it will take this, and it will give one e to t to t, and then the whole thing goes up like a pyramid. And now we shall check whether this makes sense or not. We understand that this must be a t because the whole thing, the entire thing, is a sentence. And what is the type of this thing? Just this much, excluding these two. This expression is doubly unsaturated. How is it unsaturated? This expression, you see, there is one lambda expression with an e to t type, another lambda expression with an e to t type, then it is saturated. We see whether this is satisfied. Now you see it is e to t, yes. So first it takes this e to t, then it is once again e to t, that takes this e to t, so the second one, and then it yields a t. We are perfectly happy with this. What about this expression? Now this is saturated once. Why? Because there is one lambda expression with one e to t. So we can see it goes all the way up. It is one e to t, which is perfectly all right. And then down there we have T, which is this. So we can also determine the type of this thing. It will actually be a T to e to t to t function of this thing. So this will be a very complex one and all that stuff that we can see. But one thing is sure, that we can see the types of all these things. Now, as I said, it is the second problem. I find it very interesting. It is there on page 1110 in our textbook, that is Doughty-Wall-Peters. It starts this way, the problem: a red chair. How do I place a red chair? It has got two different attributes, right? Red chair. So it is a red thing and it's a chair. So you can easily give this type e to t to red, because all red things will belong to it. But also good looks very similar, right? You can also say good chair. Also, although syntactically it looks very similar, the analysis, the semantic analysis of it will not be similar. It will be very different. Why? Because there is nothing like the set of good things. For example, a good pianist need not be a good actor, and vice versa. What does it mean? There is no set of good things. You can't say that a good chair belongs to the set of the intersection of good things and chairs, right? So that's the problem. It is because some of the good things will be in this group, some will be in other group, and all that stuff. There is no group of good things. So now our problem is then how to assign a type to adjectives like good or clever, as in good pianist, a clever athlete, or something like that. So I read the problem and then we try to solve it. Show how one could deal with this problem by assigning such adjectives to the category. So they have given us the category e to t to e to t. What would be the appropriate form of the semantic rule for complex common noun of this sort? Note that necessarily every good pianist is a pianist. Use L lambda to state the fact about the semantic value of good. This should be italicized, which guarantees this. So this is the problem. Now we need to solve this. First, let us look at the problem. As we said, let us have this syntactic construction. Let G allow. Let G be there. Let us allow G to be prefixed to P and A. P and A are 1 plus predicates. We can see that this is our model, old model. I just modified it a bit. I interpret P as a pianist and A as actor. So I can write A is a pianist and A is an actor. We just add this two, and G, whatever A means, A is a good Q. Q is once again it's a predicate variable. So let us have this syntactic category which can be prefixed to a 1 plus predicate. Now our problem is how to give it kind of a semantic rule, and how to give it a semantic structure, especially a lambda expression. We'll try to do that. Look at our set. Both A and B are pianists. A and B are things. Their names are J and D. So it is true that P J and P D. It is also true that from this we know that A D and A N, right? But among this D, I'm now calling these things by the names. So the problem is that we can see that D is a good pianist, whereas J is not, and N is a good actor, whereas whereas D is not. So this is our problem. Now, how to? So that is the reason there is no entity of good things, because that entity will a category of good things, because if the the category is problematic because it may have a good pianist, but then it may also have a bad actor who is a good dancer, right. So the problem is, then where is the category of good things, right? We can't have that category. So now let us assume that D is a good pianist and N is a good actor. In that case, how to assign some form, some structure to this, to G. This is our solution. This will be the structure of G. How? We have actually described the facts that we already stated, and then how to understand this. Had it been a function, had G been a function, not G, the value of G, had it been a function, it would be like this. So it would have A, B, C, A and B. So what is pianist? A and B are mapped to 1 and C is mapped to 0. This is the function pianist, and once again A, B, C, A and B, A is mapped to 0, B and C are mapped to 1, and then this is mapped to once again A, B, C. You see who is good? B is good. So this is mapped to 1, but these two are mapped to 0, and once again A, B, C, and here C only is mapped to 1, others are mapped to 0. So this would be the functional structure of the value of G, and this would be the set structure of the value of G, that we can see. And also it is another exercise where we can convert a new type of function into the set talk, whatever we call it. Now how will it work? It will take, so good pianist will first take pianist and it will give this, and then it will take whatever G or D and it will take here and it will give a value. So this is the structure of it. So now how will it work given this functional structure? So for example, let us look at a false sentence, that is J is a good pianist, right? We just write G, P, J. We know it is false. So first it takes, I'm just putting it here, so it actually should be here, but there is no space. So we are giving the value of P here. What is the value? It is this A, B, C, and this will be 1, 1, 0. After that we give the value that is, what is J? J is actually A. We can see that first it will take this and yield this. This will take A, and finally it will yield 0. So we can check this, and the lambda expression of it, obviously the lambda expression will be like this, and if we want to have it will be e to t, and sorry, this is e to t to e to t, because this is G, this is e to t, and this is E. So the structure, this much is t, and then e to this also will be t, and then this will be once again. So it's because it's the same thing. This is e to t to e to t to t, because this is a sentence. So we can understand that we derive it from this, and we can understand that this is a lambda expression for good, where q is a predicate variable, x is an individual variable or variable of type E. Thank you.